Hi, everybody. Welcome back to 19b.
If there's a place you gotta go, I'm the one you need to know. I'm the map. I'm the map. I'm the map. If there's a place you gotta get, I can get you there, I bet. I'm the map. 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 I'm the map.
Okay, is that driving you crazy yet? Yes. Oh, man. I can't tell you how many days I heard that song in a row when I was taking care of my kids. They've grown up and love that show, if you know which show I'm talking about. So, have you started your map? Again, keep trying to do it. It's a great idea. Okay. Here's another one I'd like to show you. This is from Leah4Sci, as you can see, .com. She has really, she has one of the best websites that kind of breaks down organic chemistry into very simple terms. So if you ever want to get another explanation for any complicated thing or anything I say out of my mouth that just is like, what was Nick talking about? Maybe check out Leah4Sci. Okay. All right. Besides, and again, it's a very complicated roadmap and has reactions on this one that we don't actually even do in this course. So please don't actually go and find another roadmap to use. I highly recommend you make your very own. It's the only way that it'll make sense to you. All right, let's play. Today's sites in Oregon. Yeah, we could be going to the Sports Center or the new Science Center or the Davis, but I thought we'd enjoy going and visiting how to make some ethers and esters, which we already saw a little bit in the last video. So some of these are new. I'd also like to point out how we are canceling out this whole ether synthesis here with phenols because you already know how to do it, and I would treat it the same way essentially as you do with alcohols. So we're going to leave this one alone. Okay, let's go play. Preparation of some ethers. How do you make ethers? Well, Williamson, look at that strapping young lad. He came up with one of the two major methods that are used today to make ethers. And we need two methods because one involves using a primary carbon only with the leaving group, alkyl halide, for example, but only works on a primary carbon. You should know why. Why would this alkoxide, strong base, great nucleophile, only work well to produce this ether on a primary carbon? And if you forget how to make alkoxides, wait, I can't wait to show it to you again because I love showing any movie that shows an explosion. Yes, so if you want to make your very own alkoxide, in any synthesis, step one would be writing the alcohol and then adding pure sodium metal. I want you to recognize that this is a redox reaction. I will never ask you, or should you ever be required, to show the reaction mechanism for this process. This involves internal electrons transferring from one atom to another. So very hard to show with a two-headed arrow electron movement. But very exciting to see explode, right? I love seeing that thing explode. So cool. All right. So remember, you can make your own ethoxides, not just sodium ethoxide, but any ethoxide or alkoxide, excuse me, from any alcohol that you want to play with. And therefore, you can use that to react with any primary carbon to produce your ether. Just remember that this one would be on a primary carbon. Okay, cool. So how would you synthesize this ether, known as ethyl isopropyl ether? What would you do? Take a second and figure out and show at least one method for making this ether. Got it? Cool. Gotta try, otherwise we never know. And so these are the two possible ways you can make the ether, and I like to write them out and then analyze which one would be best. So one way is putting the oxygen on the green ethyl piece and the leaving group on the blue isopropyl piece. You could always switch those two and put the leaving group on the green ethyl and the oxygen alkoxide on the blue isopropyl. Which one of these two now, as you look at it, do you think would work best? I agree. Yep, I'm right. I am totally with you. I totally agree that this is not a primary, but a secondary, and therefore is going to go big time E2 and not make my ether at all. So let's go to the other side. Let's go over there and do the synthesis on a primary leaving group, because you had the choice of either one of these. So in designing this synthesis, you should pick the two molecules on the right. Okay? Great. Let's see if you can put that to practice. Let's play around in Ether Town. So see if you can select the reaction that would most effectively produce the compound listed here, and also see if you can write the reaction products for any of the other ones that don't. What else would they make, if anything? Okay, and we'll come to class and take a peek at your answers. I love going to study groups and seeing what you got. So please write up something. All right, now method 2. This one is, again, not for primaries, but definitely starts leaning towards the secondaries and tertiaries. And that's because when you look at this process of trying to take this tertiary, and let's be clear, this is a tertiary benzylic carbon that this chloride's attached to, that really a tertiaries can't do SN2 reactions. So we're all still in chapter 10, but we're still playing around with the ideas of chapter 8 and SN1 and SN2. So keep asking me questions about that chapter if you still have issues determining SN1 or SN2, because this is a clear, flat out SN1 reaction that would love to go with this poor nucleophile that's not negatively charged to create this ether. What's really also helps this reaction along is I have actually put the solvent that is my nucleophile in the reaction. So solvent is the majority of what's in the solution, and therefore if the majority of my solution is ethanol, then imagine how many times this chlorinated compound will be able to bump into an ethanol and do an SN1 reaction. Lots. So we like Sovolysis reactions. These actually increase the rate of our reactions and increase the amount of product we're able to produce in our reactions. Okay? Take a second, try this one. Careful, be observant. Notice that note. But that's because whenever you do SN1 and form a carbocation, I want you to follow that advice every time. Careful, be observant every time you make a carbocation. Pause, give it a shot. Okay, hopefully you wrote something down, got a possible answer. Let's see if it matches mine. This is what I came up with. Whoa, what happened? The ether is no longer not on this carbon, not on this secondary allylic. But hopefully if you gave the last name allylic, that might chime in that there's a possibility for resonance. And so the carbocation moved to the tertiary allylic carbon. And by doing so, then the actual poor nucleophile ethanol reacted with the tertiary allylic carbon. Okay? All right. What? Whoa, what is this? Cyclic ethers? Wow. Okay, because they're not always just straight chain ROR. Maybe I can make a cyclic ether, and even better yet, maybe I can make a weirdo ether that is in the same molecule. Maybe if I start with the leaving group and the attacking nucleophile or other oxygen piece in the exact same molecule, I might be able to make an ether. Now it's very important to do these intramolecular reactions. We talked about how 5- and 6-membered rings are most prevalent, but when you're making cyclic ethers, they actually work really well with also with 3-membered rings. So closing this off, 1, 2, and having it attack this blue squared carbon at 3 making this three-membered ring is actually very, very easy for this molecule to do, and it will happen very quickly. All you have to do is throw in some base that helps abstract this proton to create a negative charge, and notice here why it has to be trans. It has to be trans to the leaving group because what I'm about to do is a huge, big old SN2 reaction on that carbon. And therefore, if I'm doing an SN2 reaction, it has to do a backside attack. Dun, dun, dun. Back from where? Back from trans. Trans from front to back to front. The leaving group and the nucleophile in this cyclization to make this epoxide, is what this new little group is called, has to be trans to one another so that they can do a backside attack here, kicking off the chloride. And notice that makes both of the bonds wedges because they're on the exact same side. Pretty cool. We're going to see how these epoxides are incredibly useful in future syntheses and will become a fairly significant town that has a few arrows coming off of it, of its own. Okay, so it's really helpful to be able to start with halohydrins. This one is a chlorohydrin, or bromohydrins are fine too, but you start with these trans halohydrins and you can make these beautiful epoxides, these cyclic ethers. Okay? So, big message here, they're favored over almost everything, even acid-base reactions that might occur elsewhere, because intramolecular is really fast, and also forming three-membered, five-membered, and six-membered rings creates very stable molecules. All right, and if you want to know how stable, you should just ask your friendly female gypsy moth, who actually biologically produces this amazingly huge epoxide to attract males. I wonder if my wife's got some of this stuff around. I don't know. I'm pretty attracted to her. Okay, so who knows? Female, lots of biological active molecules have these cyclic ethers. So keep your eye out for them. Let's play. How do you synthesize these ethers? Again, you have two R groups. Which piece has the leaving group? Which piece has the nucleophile? That's what you need to figure out and play with. So I'll pause and then I'll show you my answer. Okay, so you paused, tried out all of these. You now are about to see my answers in the best way I think it is to synthesize these ethers. So for the first one, I think you should use a phenol and a tertiary leaving group and let this just go by an SN1 reaction, because if I tried the other way, notice I'm putting the leaving group on a benzene ring. No reaction on benzene rings for nucleophilic substitution. So not happy. How about the next one? Again, I'm using the same T-butyl bromide and letting my alcohol do a little SN1 reaction on this, because if I switch it and did it the other way around, I'd have to put my bromide, oh wait, did I do that right? Oh, I think I put it on, I missed it. That's not quite the right structure, sorry. But you'd have to be putting your bromide on a primary, but that's a big, huge, bulky base. This does E2 only. So this one's a bummer, even though I wrote the wrong structure. Sorry. So how about the last one? Oh, three-membered cyclic ether. So did you draw the correct stereochemistry for the trans halohydrin? This is how I might have drawn it to keep it so that I can see that the bromide, the leaving group, and the oxygen are trans to each other. I draw them in the same plane of the paper and then deal with the wedges and dotted lines so that when it cyclizes, it pushed the hydrogen down and the methyl down to put them into these places, but didn't switch their sides. Now, granted, this is the way I drew the starting material. You could have also drawn it this way and, you know, like that, and that would have been fine too. That is the correct stereochemistry for this specific epoxide. So epoxides are a little tricky. They involve stereochemistry sometimes. Your favorite subject? Yes. Okay. So last but not least today, what about preparation of esters? Why should we care about making esters? Esters, who cares? Ethers? Cool. Alcohols? Cool. Esters? Cool. Look what esters can do. Esters are smelly. You can take an alcohol with a carboxylic acid and create any of these different little fragrances. And especially some of these are used to make perfumes, food flavorings. This is a huge industry that makes millions of dollars, billions of dollars every year as chemists discover ways of synthesizing how to make an apple smell without actually squeezing out all the juice of an apple and putting it in some food flavoring. So it's kind of cool. Esters have a way of triggering our sense to create these smells. So how do we make them? You already know. You've seen it before. It was the very first step in our secondary alcohol synthesis. This was on our way to our secondary alcohol. Sorry. So you've already seen how to take a specific acetate to make this ester, okay? So this is one thing to keep in mind. You can have any chain here. This can be any R group, as long as you need it. As long as you have the C double bond O minus, you have made a nice weak base, great nucleophile, and it will react in an SN2 fashion. So just make sure this is primary or secondary to avoid that dreaded tertiary SN1 reaction. Oh, look, I'm reminding you again. Sorry, sometimes I forget. All right, pause the video here. What product would you make for this molecule? Ooh, we had lots of pauses today. So did you draw this product? Do you have the correct stereochemistry? Remember, backside attack. If there is a chiral carbon, we need to pay attention to that chirality. So this is the product I produced. All right, having fun yet? Let's have some more fun. Even more fun. Oh my gosh. All right, show me the reactants for this first synthesis. What would you use as two reactants? And what would be, whoa, what is that? Some huge molecule on the bottom over there. What product do you think would be formed from the reaction on the bottom over there? Okay, pause. All right, you ready to see my answers and what I would use? So on the top, I would use and put the OH group on the actual vanillic carbon. This does not do any, I can't do it the other way around because that vanillic carbon does not do any SN chemistry at all. So the alcohol has to be placed here. And I put it on a secondary, and granted, I don't want to use O minus or I would get elimination. So even though this isn't really fast, this is probably a one-step synthesis is the easiest way to do this and create my final product. Okay? Again, I'd also probably want to do this at room temperature or 0 degrees Celsius to avoid the dreaded E1. And hope that this just goes a nice, gentle SN1 for me. Okay, how about that bottom reaction? What the heck is that? Well, spy in all of those carbons and molecules, there is only one leaving group that's possible for you. And I have a beautiful acetate for you to do a nice, beautiful SN2 on it. Why did I give you this one? This molecule is actually known as trenbolone acetate. What's so special about this? This is a steroid. Steroids have this general structure right here with slightly different pieces left and right on them, but they have these 4 cyclic rings. And this specific steroid is heavily used in the production of beefy cows. People want to get more meat out of their cows. They feed this steroid to the cows, and the cows get beefier and beefier, and they can have what are really huge and humongous cows. They're kind of grotesque. If you've ever seen a beef cattle, they're not just like your normal Jersey cow that produces milk. They are freakish, and it's because of the steroids that they feed these animals to bulk them up. Kind of scary. But I hope I didn't scare you out of the next steak you're going to take, because maybe you just get a nice organic one. No steroids used. Okay. All right. Let's clear our mind of that beefsteak cow. All right. Let's have some more fun. Here's an interesting exam question that was popped off some other professor's exam. I thought I'd show it to you because it has different language than what I normally would use in my questions. But you should be able to read any kind of Orgo language, translate it, and see if you can come up for an answer on this one. So bring your answer to this question and even any questions you have about the question to our class, and we'll check it out. Can we have even, whoa, there's no way we can have even more fun in Orgoland, or is there? Let's see if you can propose an efficient synthetic pathway for this conversion, meaning you can have multiple steps, but after each step, please show the product of each step on your way to going from this chiral alcohol to this chiral product. Okay, this chiral ester. Cool. All right, last but not, what? No, too many problems, Nick. I can't handle it. Well, you know, just in case you want to play around some more. I always feel bad that roadmap problems only come up right before exams and you kind of get inundated with them. So what I'd like you to do is try this roadmap problem that actually relates to the chemistry we've just been talking about, and see if you can merge the two, because that's what roadmaps are all about. Not just seeing if you can understand mass spec, but seeing if you can take the chemical reactions that are happening in a roadmap problem and use that information to help you figure out pieces and parts of your structure that must be there, because some of these reagents only react with very specific functional groups. Have fun playing with this. I can't wait to see all the possible answers to all these class questions. Please, please, please post them in our Jamboards. Okay? All right. I will definitely see you soon. Bye.